What specific problem does the COND P-DIFF method aim to solve in the realm of parameter generation for deep learning models?
The COND P-DIFF method aims to solve the problem of synthesizing high-performance model parameters conditioned on specific tasks in a practical manner. Previous methods in parameter generation faced limitations such as insufficient parameter scale for complex applications and a lack of support for conditional high-performance parameter generation. By utilizing a conditional latent diffusion model, COND P-DIFF addresses these challenges by generating novel LoRA parameters that are tailored to specific conditions, thereby enhancing the efficiency and effectiveness of fine-tuning large pre-trained models. This approach not only reduces the computational cost and time associated with model optimization, but also ensures that the generated parameters exhibit comparable or superior performance relative to those obtained through conventional training methods. Ultimately, COND P-DIFF provides a promising direction for task-specific parameter generation in neural networks.
How does the proposed COND P-DIFF method work? Please illustrate step by step, detailing the process from parameter extraction to generation.
The proposed COND P-DIFF method operates through a systematic process that involves several key steps. First, it begins with parameter extraction, where an autoencoder is trained on a dataset of model parameters fine-tuned using low-rank adaptation, LoRA. This autoencoder captures latent representations of the parameters, allowing for robust reconstruction of these weights. Next, a conditional latent diffusion model is trained to generate high-performance parameters based on specific task conditions, such as text or style images. During inference, random noise and task-specific conditions are fed into this trained conditional diffusion model, which generates latent representations. Finally, these representations are processed by the decoder of the autoencoder to produce new, high-performing model parameters tailored to the given conditions, effectively synthesizing parameters that differ from those obtained through conventional training methods.
Can you provide a simple and illustrative example demonstrating the inner workings of COND P-DIFF? Walk through the main algorithm steps using an example to explain the process clearly.
To illustrate the workings of COND P-DIFF, let's consider an example where we want to generate LoRA parameters for a text classification task using a specific condition, such as a task description and two-shot examples. First, we begin by fine-tuning a pre-trained model using LoRA on a dataset, collecting various checkpoints of the model parameters during training, which we denote as theta equals theta_1 L dots theta_n. Next, we train an autoencoder to extract latent representations from these parameters, effectively compressing the information while maintaining essential features. Once the autoencoder is trained, we then utilize a conditional latent diffusion model. For our specific task, we encode the condition, task description and examples into a domain-specific representation. The diffusion model is trained to generate new latent representations conditioned on this input. During inference, we feed random noise and the encoded task condition into the trained conditional diffusion model, which generates new latent representations. Finally, these representations are decoded back into the parameter space using the autoencoder's decoder, resulting in high-performance LoRA parameters tailored to the specific task conditions. This process highlights how COND P-DIFF synthesizes novel parameters rather than merely replicating existing ones, demonstrating its effectiveness in generating task-specific model weights.
What are the main theoretical and practical benefits of using COND P-DIFF over existing parameter generation methods like G.PT and P-DIFF?
The main theoretical benefit of using COND P-DIFF over existing parameter generation methods like G.PT and P-DIFF is its ability to perform conditional high-performance parameter generation, which is crucial for real-world applications. Unlike G.Point, which has been evaluated only on simple datasets and lacks generalization capabilities, and P-DIFF, which does not support conditional generation, COND P-DIFF synthesizes parameters tailored to specific task conditions, enhancing its applicability across diverse domains. Practically, COND P-DIFF significantly reduces computational costs and time associated with model optimization by leveraging a conditional latent diffusion model, allowing for the generation of high-performing parameters that differ from those obtained through conventional training methods. Additionally, the method demonstrates superior performance and robustness across various datasets and architectures, as evidenced by extensive evaluations. Overall, COND P-DIFF not only addresses the limitations of previous methods, but also provides a promising direction for task-specific parameter generation in neural networks.
How was COND P-DIFF validated or tested in the experiments? Please explain the datasets, experimental design, and performance metrics used in the evaluation process.
COND P-DIFF was validated through a series of experiments across various domains, specifically in natural language processing (NLP) and computer vision (CV). In the NLP experiments, the model was tested on the GLUE benchmark, utilizing 150 training samples from models like BERT, RoBERTa, and GPT-2, which were fine-tuned using LoRA. For the CV tasks, particularly style transfer, datasets such as SEMArt and WikiArt were employed, with performance evaluated using the Frechet inception distance (FID) metric, where lower scores indicate better image generation quality. The experimental design included generating 20 LoRA parameters for each task using the conditional diffusion model and merging these parameters into pre-trained models to assess their performance on validation datasets. The results demonstrated that COND P-DIFF consistently yielded comparable or superior performance relative to baseline methods, validating its effectiveness in generating high-performance parameters tailored to specific conditions.
What specific results were achieved with COND P-DIFF, and how do they compare with baseline methods in terms of performance and efficiency?
COND P-DIFF demonstrated the ability to generate high-performance parameters tailored to specific task conditions, achieving comparable or superior performance relative to models trained with conventional methods across various datasets and architectures. In the NLP experiments, COND P-DIFF consistently yielded comparable performance to baseline methods on the GLUE benchmark, indicating effective learning of conditional parameter distributions. For image style transfer tasks, the method efficiently synthesized style-adapted LoRA parameters, resulting in lower Frechet inception distance (FID) scores, which signify better image generation quality compared to baseline models. Additionally, the ablation studies revealed that task normalization and the size of the training dataset positively impacted performance, further enhancing the efficiency of COND P-DIFF. Overall, the results highlight that COND P-DIFF not only generates novel parameters distinct from original training data, but also maintains a robust performance across different tasks, showcasing its practical applicability in parameter generation.